Got it. All right. Thank you, everyone. Thank you, Sergey. So today we're going to discuss the special topic of learning physics from images as part of the Virtual Summer School of Machine Learning and Electron Microscopy. So really nearing the end of this course. This is lecture number 23. And today I'm going to give you a flavor for what we actually do when we get images, typically atomically resolved images in electron microscopy. It doesn't have to be, but we're going to focus on that today. But the point here is that, traditional experiment theory matching has been done in sort of macroscopic measurements, right? So you sort of have a simulation that gives you some idea about how your material system as a whole behaves, and then you get some measurements, and these measurements are typically macroscopic in nature. So for example, let's say that you have an alloy, then you do a stress strain curve, you find the Young's modulus, you find energy densities and so forth, elastic energies that you can get from this. And then you compare it to some simulations, and then you can get some insight and predict how the material might behave under different conditions. Now, when we actually have electron microscopy images of materials, we can't generally do this kind of model matching anymore. And I'll get into why that is the case, and then also how we solve that particular problem. It's actually relatively unexplored, I would say, or not unexplored as such, but rather less explored than probably it should have been. But we'll give you our take on how we do this sort of model matching in terms of atomically resolved images themselves. And so, as you saw from my last lecture, I'm from the Center for Nanophase Material Sciences at Oak Ridge National Laboratory. So let's get started. So every day, as microscopes get better and better, we collect more and more high resolution imaging data, right? And a lot of the time we can directly see things like order parameters. So for example, if we look at ferroelectric materials or ferromagnetic materials, we can often get these sort of very nice atomically resolved maps of what the polarization looks like, right, as it goes through the sample. And so you can see in this case, these sort of closure states in bismuth ferrite. You can see some very nice sort of vortices and anti-vortices and arrays of such topological defects in superlattices of ferroelectrics that are carefully grown. But the point is that these sorts of images are now not necessarily routine, but certainly relatively straightforward to acquire on many different kinds of samples. Similarly, with scanning tunneling microscopy, you can have a look at individual atomic scale defects, and you can manipulate defects with scanning tunneling microscopy. And so we're collecting these kinds of images every single day, right, of thousands of microscopes around the world. And so while image analysis techniques are sort of well developed, right, I think there's only a limited amount of transferable material science knowledge that we actually gain from looking at these, from analyzing these images in more traditional routes. And so what we really want to do is really find out what an image actually encodes. And what it actually encodes is largely encodes the physics of the system. And we want to be able to extract that physics. So how do we do that? By looking at these images and applying data analysis techniques. And so that's really what the focus is going to be today. And so the first thing is, we're just going to talk about data-driven approaches. Let's just have a look at what we can gain from images purely from sort of computer vision type of techniques. And the reason why we want to do this, right, why we want to image structures at all is really because for a lot of materials, right, for things like complex oxides, the physics itself is inherently local. So this is an image that I captured about 7 or 8 years ago of lanthanum calcium manganite with scanning tunneling microscopy. And so this is a relatively large scale image. It's about, I think, 50 by 50 nanometers, or maybe even larger. But you see these sort of very interesting structures on the surface. You see two different kinds of terminations that we're seeing. In other words, different heights here. We see also different kinds of reconstructions that are present. Like you have one kind of reconstruction here and another one that's sort of here. I don't know if you can see my cursor. Maybe I should use my pointer. You can probably see it now. So you can see one kind of reconstruction over here. This is sort of rotated over here. You see another kind of reconstruction that's here. And so what we are looking at is that if we actually measure the spectroscopy, right, in these different positions to try to understand electronic properties, then it's really going to be dependent on the kind of reconstruction that we are actually in. And so the physics that we're getting here is actually very local, right? Depending on the surrounding structure, we're going to get slightly different kinds of electronic properties in that particular part of the material. And so if you actually look at the way that crystallography as a field has progressed, right, one of the real downsides of crystallography in the last 100 years, and this is relatively well recognized, is that there is a a real gap in terms of being able to understand materials where this kind of reconstructions actually happen, where the material can no longer be described as some kind of macroscopic average in terms of its crystalline structure, right? You have a large amount of disorder, and that disorder really has, in some cases, correlations. And so we lack an understanding of how to describe these kinds of correlations at the local level. And so what we really need is a language that we term local crystallography, right? So can we look at each atom and its surrounding neighbors and compute statistics on this, and to be able to better understand what it is that we're actually seeing in this material system, okay? What's a simple way to do that? Well, the simplest way to do that might be something that we borrow from computer vision techniques, and that is called sort of texture analysis. And so what is texture analysis? Well, texture analysis is really just showing you what kind of textures are actually available in any kind of image. And so in this case, this is another image that I captured on a manganite with scanning tunneling microscopy. And so you can see in this case, there are two different kinds of terminations. This happens to be the lanthanum calcium oxide termination, and this one happens to be the manganese oxide termination. Doesn't really matter for the purposes of this case. But basically what we want to do is we want to try to identify these particular phases, right? The phases that are actually present in our image, and then identify the spatial distribution of those phases. And this can be quite helpful as, for example, we're looking at changes as a function of, let's say, temperature or pressure or some other kind of external variable, as these structures may actually change dynamically in time if we're modifying our material system. So in order to do that, we generate something called the sliding window transform. And so that's actually described here on the left-hand side. So what you see here is you see a small window, and this small window is typically on the order of, let's say, 16 to 32 pixels, assuming that, you know, this image is about 128 or 256 pixels. It can be generally on the order of, you know, 10 or 20, 30 windows that can go across this particular image in any row. And so what we do is we take this window, we slide it across the image, we capture the local image, right? And then we sort of stack it together. And what we do is that we can apply different transforms to this particular local window. So for example, I can capture a local window here, and I can do the fast Fourier transform or 2D fast Fourier transform, so-called FFT analysis on this particular window. And so now I can generate a stack of windows which have been applied, to which we have applied the standard FFT algorithm, right? So now we have a sort of four-dimensional data set. So we have initially a 2D data set here, but after we do this sliding window transform, we have a four-dimensional data set where each particular slice here is a new 2D Fourier transform of one of the regions of this particular image, right? And so what we can do from this is that we can then take these 4D image data sets, we can push them back to 2 dimensions, right? We can reshape them into 2 dimensions, and then use something like certain algorithms for unmixing, right? This particular data set, things like independent component analysis, principal component analysis, Bayesian linear unmixing, or the algorithm that I'm going to describe here, which is called nFindR. Okay. And let's describe that. So just again, iterating how this actually works. Let's say that you have multiple phases in your particular image. This can be different kinds of domains in your sample, different kind of atomic arrangements in your sample. But basically, this is a very unsupervised method. All you have to do is you have to say, I want to do the sliding window transform, and you can use our hygroscopy methods to do this. You can then generate these 2D stacks of FFT images. And then from these 2D stacks of FFT images, you can do some analysis in terms of things like nFindR. And so by applying this nFindR algorithm, it will retrieve for you the constituent phases, phase 1, 2, 3, 4, and then it'll give you their spatial abundances, right? Where they are actually present within your particular material system, right? Within your particular image. How does this actually work in practice in terms of this algorithm? And so the algorithm that we're going to describe here is something that was developed in 1999 by Michael Winter. And so it's really a unmixing algorithm where what we try to do is we try to assume that we can reconstruct any of the individual members of this data set, right? Any of the individual 2D FFT transforms as a linear superposition of other so-called n-member spectra, right? So if I can choose 3 or 4 or n number of different kinds of Fourier transformed image windows, and I can reconstruct, I want to choose such n members such that I can reconstruct any number of constituent windows within our data set, right? And so it has to actually obey some certain constraints. The first constraint is that the mixing proportions of these n members must sum to 1. In other words, I must have I must have, a weighting to 100%. As a physics constraint here in terms of the coefficients themselves. And so I must be able to represent my individual spectra as some superposition of these so-called eigenspectra or these so-called N members. And so the way that we do this is relatively straightforward, right? How do I choose those particular N members? It's really straightforward. Let's say that we want to find 3 different N members, right? So what I can do is I can then project my data set into a lower dimensional subspace. Typically, this can use principal component analysis. And so every one of these dots is actually representative, right, of one of those individual windows that we calculated. And so what we want to do is we want to maximize the area of this particular plane of this particular triangle by choosing the vertices of the triangle such that this area is maximized. And in fact, this is actually a volume in higher dimensional space. So we want to be able to maximize this particular hypervolume, right? So we want to iteratively select the N members, accepting this new selection if the volume of this particular triangle actually increases. Because what does this mean? What this means is basically, if you remember things like ternary phase diagrams from your material science lectures, you know that you can generate any of the compositions, right, within this phase diagram by linearly combining these 3 N members together. And that's exactly what we're doing here. You can represent all of these particular spectra by linearly combining these 3 N members here. And so you want to iteratively find the N members that can allow you to describe most number of spectra that's actually present in your image. Okay, and so we can easily do this through an iterative algorithm with NFindR. Anyway, that's the algorithm itself. Let's just try it on a simple test case. So in this particular test case, I have two different kinds of structures, and it's very evident here. And so one structure is on the left and one structure is on the right. And if I take a global Fourier transform, what you see here is that you can actually find both kinds of structures in the Fourier transform because it's a global average of what we're actually seeing. But what we want to do is we want to find out what those structures are individually and then where they're actually located in our image. And so we can run this sliding FFT transform, and then we can do our NFindR analysis, and this is the result this is the N member 1 that it finds, and this is actually the N member on the right. This is the Fourier transform of basically the right hand side of the image, and then on the N member 2, it's showing us that there's a different kind of structure which is kind of rotated with respect to N member 1, and it is on the left hand side of the image. And that's where the abundance actually is as well. So it shows us what are the constituent phases, and it shows us where they are located within our particular image. And it does this in a purely unsupervised fashion. There is nothing that I have to input to this algorithm other than the number of N members that I want the algorithm to discover. Okay. So we can do this on a very real image of a STEM catalyst. This is actually published in this particular paper that you can look at. But basically, we can find, for example, a vacuum region. This is sort of shown on the right-hand side here. You can clearly see this N member 1 corresponds to this vacuum region here. The N member 2 corresponds to the matrix that surrounds this catalyst particle. And so that's evident here. And the N member 3 corresponds to the actual catalyst particle itself, right? So this combination of this NFindR algorithm with sliding Fourier transforms can quickly and automatically determine what are the phases present as well as their spatial abundance. And in fact, we've used this over multiple different types of samples, as well as sort of in situ to EM data, where we may have changes in the number and composition of these phases, right, over time. And so this is actually a very nice method to be able to automatically track how these phases change in dynamic systems. And so that's where it becomes really useful. Of course, by eye, you could do this yourself, but if you have stacks of images and you have temporal sequences of such images, you really want something that's an automated and will give you the data about the actual kind of structural phases that are present. And this algorithm does that for you in a purely unsupervised manner. And we can also use this for things like a scanning tunneling microscopy, where you might have different kinds of electronic reconstruction. So this is images that were collected by Maxim Ziadinov on alpha ruthenium chloride. And so there is there are some fine structures in the electronic superlattice within this particular system. It happens to be a Mott insulator. Just in order for us to be able to better see what we are going to expect, at least, this is a test image of 2 different kinds of electronic structures that we actually image. And this is, again, just sort of simulated. But on the left-hand side, you see that test image. And on the right-hand side, you see the end members that would be resulting from this test image, right? So if you actually look here, the key difference between end member 1 and end member 2, that's sort of the difference between this region here and this region here, is the intensity of these 2 peaks in the Fourier transform, right? So they're very heavily suppressed. And so you can see here, of course, there's some, abundance on this side here, and then there's a much more greater abundance for end member 2, on the bottom right-hand side here, where you have this different kind of electronic structure. And so when we actually do this in a real image, what we actually find is that you absolutely see this kind of modulation of the period of the intensities of these peaks in the Fourier transformed image after you perform N-find-R and sliding FFT analysis on this particular image. So you see here these 2 peaks are very heavily suppressed in end member 2, and so we can start to find out where these reconstructions or electronic reconstructions are actually occurring, and this is evidence of dimerization in this particular system, and it was done exactly in an unsupervised manner, right? We're not looking; it's very difficult to see by eye that this is actually occurring, but by looking at the end member spectra themselves and comparing it to a test image, we can very easily now see where this dimerization is actually occurring in alpha ruthenium chloride. And so this is, again, a very nice test case of where we can really utilize very straightforward image analysis to be able to give us better understanding about the physics of the system. All right, are there any questions thus far? Okay, so that said, I want to move to the next thing. So what I showed you is just a purely unsupervised method where you might have different phases. Maybe the atoms are not particularly easy to resolve. And in that case, we're really just trying to find the positions and abundances and types of phases that are present in our image. But very often we also can find the atoms, right? We can find every single atom in the image, or at least most of the atoms that are in our images. And so what we would like to do as a purely data-driven method is to come up with this language of local crystallography, right? So can we come up with the statistics of the positions of these atoms? And rather than having a look at local or global Fourier transforms, we can actually do this from the perspective of looking at each individual atom and its neighborhood, right? So let's say that I have an individual atom here. I can look at its, for example, 6 individual neighbors. I can calculate the distance to each of those neighbors, and then I can calculate the angle to each of those neighbors. And so now I have basically a 2-dimensional matrix where I have each individual atom, and I have the distances and angles to each of those atoms' neighbors, and each row is a new atom that I'm looking at, right? And so we can very easily calculate what these statistics are, and then similar to our N-find-R method, we can also compute different kinds of unmixing algorithms or matrix factorization algorithms to better understand what are the distributions of neighborhoods within our particular material image. So one example where we did this is the MOS2 RES2 system. So this is a system of 2D materials where we alloy molybdenum with rhenium. And so there's actually a structural phase transition that occurs between a so-called H phase and a T phase in the rhenium sulfide system. This structural phase transition requires the existence of broken bonds and defects. And so one of the outstanding questions in the system was, does this transformation occur globally from some kind of from composition changes, or is it locally driven, right, based on the surrounding rhenium atom density? And so on the left-hand side, you see, molybdenum sulfide with a few atoms here of rhenium, very few. And so it's really just maintained its sort of MOS2 structure. This is so-called H phase. And then as you change and increase the composition of rhenium as you go across this particular image series, you can see that clearly you see some kinds of very interesting modulations of the structure as it transforms from this H phase to this T phase. And if you actually look at, the Fourier transform, it becomes quite obvious that here you have kind of a nice, a very nice clean Fourier transform with only one kind of structure, and once you start to alloy with significant quantities of rhenium, you start to see a peak splitting that's occurring, and then that sort of splits entirely, and so now it becomes the full T structure on the right-hand side. So we wanted to better understand how this phase transition is actually occurring in these samples. And one way to do that is basically to identify every kind of atom in the system. And we can very easily do this because these are nice STEM images. So we can use Atom AI, for example, try to find and use deep convolutional neural nets to be able to tell us where the atoms are and extract those atomic coordinates. But once you have those atomic coordinates, what we can do is that we can compute principal component analysis of those neighborhoods, right? So let's say that I take each individual molybdenum atom and then look at its neighbors. You can see that I then compute the principal component analysis of each of these neighborhoods, right? So I have a large matrix, and then I compute the PCA of that particular matrix. And when I actually plot that, what it actually shows is the so-called, something akin to sort of normal modes, right? What are the modes of distortions that are present that we are actually seeing? And so if you look at this particular component 1, you can see that there's sort of expansion or compression of the lattice. This is just generally a chemical expansion term. The second component is interestingly a sort of seems to be correlated with that symmetry breaking, right? So you sort of see that two of the nearest neighbors are moving along one direction, and then two of the neighbors are moving along the other direction. And so there's clearly a breaking of this hexagonal symmetry that's occurring with this PCA component 2. PCA component 3 is a little bit more complicated, and we won't really discuss that. But let's just focus our attention on this particular symmetry breaking mode here that we've discovered using principal component analysis of the atomic environments or neighborhoods in this particular system. We can also plot where this is occurring, right, in terms of the scores of the PCA component 2, and so you can see where this is larger and where this is smaller. And interestingly, there seems to be some kind of bifurcation. In other words, we see two different kinds. We see two different lobes in the intensities of this component with respect to component, PCA component 1 versus 2 with respect to component 1. So what this is telling us is that there's two different distributions with respect to component 1 of component 2, and that will become very evident in the next slide. Because what we wanted to do is we wanted to try to find out, right, where this component 2 is actually showing up with respect to the compositions that we're looking at. So if we look at, the first component, and we just plot the scores for the first component as a function of the number of nearest neighbors of rhenium atoms, right? We actually see that, and we color them by the composition that we have of our global sample. Then you see that, more or less the component 1 doesn't really have a strong dependence on the composition, right? So you sort of see every color here is sort of mixed. But in terms of component 2, what you find is that as you increase the numbers of the number of rhenium that's present, right, you actually see the sort of bifurcation that's actually occurring. So we expect, obviously, that when we go to compositions like, MO 0.05 and rhenium 0.95, that obviously when we look at our molybdenum neighbors, we're going to get a lot more numbers of rhenium atoms in our neighborhood, right? So what that means is that we're going to get a lot more statistics around these edges. But what we also see is that even when we have small numbers of rhenium neighbors, right? So systems like rhenium is only 0.55 and molybdenum is 0.45, we still see some mixing of the colors here. And so, but what we see is that although the colors are mixed, we see that the scores themselves are sort of bifurcating, right? We're starting to get increasing values of our PCA score for component number 2, right? And so this is really interesting because what it suggests is that although our compositions can be, the composition dependence is not particularly high, the score, the principal component analysis score is very dependent on the number of nearest neighbors of rhenium itself, right? So this is very important, right? Irrespective of composition, we seem to have an effect that is dictated by the local chemical environment, right? Not by the global composition that we actually have. And so this is really important in terms of understanding the drivers of this particular phase transition. If you want to read a more detailed analysis, you can read this particular paper that we published a couple of years ago. But we can also take, for example, more statistics of these images and try to find, for example, what is the probability that we are going to find, a certain nearest number of rhenium atoms based on the composition that we have. And then we can compare that to things like what is the, if we create some kind of Gaussian mixture model with molybdenum neighbors, what is the probability of finding, for example, high scores of this symmetry breaking transition based on the number of nearest neighbors of rhenium that we actually have. So the long story short here is that this is getting a little bit technical, but we can quantitatively match the symmetry breaking distortion to the local chemical environment in this particular system. And we can find that we have a strong statistical predictor of the phase transition based on the local chemical environments themselves, which are better predictive, which are more highly predictive than actually the chemical compositions themselves. And so this allows us to be able to look at the drivers of phase transitions just through looking at local atomic analysis across a composition series, right? So we haven't actually had to do any simulations in this case, right? We just looked at what the data was showing us, and we tried to predict whether the global composition is a better predictor of the symmetry breaking transition, or whether the local chemical environment is a better predictor of that transition. And so clearly, from this study, it shows that although there is an effect of the global composition, it's quite small with respect to the effect of the local chemical compositional changes that we can actually see in the sample. But we can also now start to take these images, atomically resolved images, and compare them to actual models, right? So here's a really simple example, right? So one simple example that we have in growth of material systems is the so-called Ehrlich-Schroebel barrier. And so in this case, let's say that you have an atom that's on a particular surface, right? As it's sort of hopping along the surface, it might get to the edge of this particular surface, right? So this is another layer on the sample. And so in thin film growth, we call this a so-called Ehrlich-Schroebel barrier, where there is a difference in energy between the hopping that occurs on a termination versus the hopping that's occurring between the terminations, right? As you have to jump across the edge. So what we would like to do often is to try to find the value of this Ehrlich-Schroebel barrier. And it can be quite difficult to compute with first principle simulations. And so the question is, can we actually just look at our images and get an understanding of what this barrier could be? And so what we can do is, again, by looking at atomically resolved images of systems where we have multiple different layers and we have atoms on the surface, we can start to quantify, right, where these edges are, where these particular islands are, and where the atoms are. And so we can start these atoms at different positions, and we can calculate the statistics of how close they are to the particular barrier edge. So you can clearly see from this image that there's a lot of atoms that are present near the step edges of this particular sample, right? So that would suggest that there is a high potential barrier for the migration of the atoms. These are oxygen atoms from one termination to the other termination. And there's also, of course, a change in terms of the potential between the two different terminations themselves, right? So we want to be able to find and try to infer what is the difference in both the Ehrlich-Schroebel barrier height, as well as the difference between the two different terminations present, right? So we can have a look at statistics on what are the atoms that are found on the Ehrlich-Schroebel barrier itself, right, on this step edge itself, and then the atoms that are actually found on the A site termination versus the B site termination in this case. And so we can very easily compute based on sort of Monte Carlo simulations with Boltzmann statistics, we can try to model from random starts of these atoms, like where they would be for different lattice energy differences and different barrier heights. And so by doing this, we can get an understanding of what the barrier height should be based on the images that we've actually acquired, right? So by doing this, we were able to find what the barrier height was, and this was actually comparable to other similar calculations that were done for similar kinds of systems for atoms in metal oxide surfaces. And so this is just an example of where simple simulations can be compared to images in order to extract something quantitative about the physics of the system, okay? But this was sort of our first foray into this work. And so we really needed to move back into a more systematic way to be able to better understand the images that we are capturing and try to extract the most out of these, right? So we don't know, for example, how well the particular model that we used was suitable for the particular test case. I mean, it was a very much a model system, and it was a very much a simple model, but how applicable was it? Like, could we actually use it to be able to predict how the system would behave for different thermodynamic variables? And so what we needed a more rigorous framework. And so we worked with some colleagues, primarily Lucas Vilcek, a few years ago, to come up with something called the statistical distance framework. And so there's a real fundamental difference between how we can approach the way that we do these studies versus the way that traditionally studies have been done, to be able to come up with, for example, phase diagrams of or functional phase diagrams of materials themselves. So traditionally, what happens is that in order to be able to compute a phase diagram, what people do is that they make many different samples, and then they measure them, for example, for different compositions and for different temperatures. And then people go back to modeling and then try to change parameters for models that can then predict or give you a better understanding of the phase diagram itself that you've actually gone ahead and measured. And so this really requires many different samples. It requires sort of measuring properties at many different conditions. It's very time consuming. In some cases, it's also sort of redundant, because for example, if you measure a property here, it's probably likely to be the same as measuring the property here, or very, very similar to it. And so you have a lot of redundancy here. So what we really need is we need a better way to be able to come up with these phase diagrams without having to do all of these bulk measurements. And is there a way to actually do that by considering thermodynamic theory? And the answer is actually, yes, there is. And so the way that we can do that is actually by atomically resolved imaging studies. So let's say that, for example, we have atomically resolved studies, right? Then what we are actually doing here is that we can actually image the microstates of the system, right? So we can look at the kinds of atoms that are present, we can look at the defects that are present, and in principle, we can use that to generate a so-called, or to create a model, a so-called generative model, right, from which we can sample, and then we can then come up with predictions for how the material should behave for different compositions and temperatures. Now, this looks fanciful, right? How can you, from a single image, then go ahead and predict a phase diagram? But the physics actually says that, if you have enough statistics of these images, it's actually doable. And I'll show you exactly why that's the case. But basically, the point here is that we can go from atomically resolved images, we can build generative models, and then we can sample from these to obtain predictions of our material system as a function of different thermodynamic variables. So for example, things like temperature, composition, pressure, so forth. So let's have a simple test case, right? Let's go back to a simple A-B phase diagram and think about what an atomically resolved image really tells us. By the way, I'm saying atomically resolved image. It could also be atomically resolved images combined with other kinds of multimodal spectral data that gives us sort of macroscopic insights as well. And I'll get to that in the subsequent part of the talk. But let's say first we're just looking at atomically resolved images, and those images can come from, let's say, a very simple material system, and I'm going to call this an A-B material system. And this is the phase diagram of the system, right? So we start with A, and as I add some B to this particular alloy, we have some kind of phase separation that occurs. Here we have a solid solution, and then here we have, for example, a phase separation that's actually occurring, right? So let's say, for here we have this gamma solid solution, and in this case we have some phase separation that occurred. If we actually synthesize a material that's here at particular nominal temperature and nominal composition, right? What is it that we are actually doing, right? When we sample from it, well, basically what we are doing is that when we say a nominal temperature and a nominal composition, that's just meaning that there's an average, right? So what that really means is that there's a distribution over the temperatures here, and there's a distribution over the compositions here, and that distribution in the equilibrium is Boltzmann, right? So basically, when we take images, we are actually taking images of the microstates of the system. And so we can actually find local regions of different composition, right? We can also find regions where maybe the temperature was quenched in slightly different temperature than what we actually have here, right? So there's a distribution here. And so by imaging the material itself, we have access to this underlying distribution. And in fact, the tails of the distribution are where most of the physics that we care about are actually encoded. And that's the key thing here, right? So the response of the system to temperature and composition is actually encoded within the fluctuations that we are actually able to image. So if we can image this, can we use this to predict the phase diagram? And it turns out that you actually can. So what do we need in order to make this work, right? So first, we need a generative model. We need some kind of lattice model, let's say an Ising model. I'll get to that later. But let's say that we have an ability to create a generative model. Then we need to compare the right kind of statistics, right? In the case of atomic resolved images, these will be atomic configurations, right? And again, in the notebook, we will discuss what those configurations are, as well as in subsequent slides. But that basically, we need to compare the right thing. And the right thing to compare is the neighborhoods of the atoms themselves, right? The neighborhoods of what it is that we're trying to image. We can make those as the so-called configurations. We can also augment this with things like pair distribution functions that are taken from scattering data and so forth. But there are different ways to compute these statistics and measure them. And then, very importantly, we need a metric to compare the model to the experimental data, which will correctly capture the fluctuations, right? As I mentioned before, what we really care about are these fluctuations. And if there are only small numbers of these fluctuations that you're actually able to image because of sampling difficulties, right? Then if you choose a metric between that will minimize sort of a mean absolute error between an experiment and simulation, you may not capture these fluctuations correctly because it's in the tail of the distribution, right? So the appropriate metric in this instance for thermodynamic systems is the so-called statistical distance. And so this equalizes the weights of experimental and statistical data and enables an appropriate comparison. And I'll describe what that actually is with the equation of statistical distance. But it is also a measure of distinguishability of two different systems, right? So you have heard about KL divergence before in some of these lectures. This is kind of similar to that, except it's a little bit more rigorous mathematically, because the KL divergence is not a technical mathematical metric between two different distributions. However, the important thing here is that this provides a measure of distinguishability, right? So when do I know when my model is indistinguishable from is fit correctly to my experiment? Well, that is when, if I sample from my model, I can't tell that there's a difference between sampling from the model versus sampling from the experiment, right? So think of it in terms of sort of a generative adversarial network case. For example, you may have heard about GANs. There's a critic, and the critic's goal is to try to determine whether a sample was pulled from the real distribution or pulled from the simulated distribution, right? That was the one that was created by the generative model. When the discriminator is fooled exactly 50% of the time, right? So it cannot distinguish between the two different distributions, then you know that it's converged. In a similar way, when you can no longer distinguish between an experimental sample and a simulated sample, then you know that you've matched the experiment and simulation in the correct way. And so that's what we actually need. We need to be able to make sure that after fitting, then we cannot distinguish samples coming from either one of these distributions. So for atomic resolved imaging, again, as I mentioned before, we need to compare the probability of imaging particular atomic configurations, right? So every time we image, we're going to get a slightly different region of the sample. So what we really want is, we don't necessarily want to match all the atomic configurations themselves. That'll be too many, of course. But what we want is, we want to find the probability of finding a particular atomic configuration in a particular image, right? So that's something that we can absolutely compute. And so what we can do is we can get, for example, in this case, an image of an iron selenide telluride system. And so here we have selenium atoms or tellurium atoms that are seen in a scanning tunneling microscope image. We can very quickly and rapidly identify these images, and we can color them based on their intensities, right? Either they being selenium atoms or tellurium atoms. And so I can identify, for example, each individual blue atom here, and then I can identify its neighbors, right? So these are the 4 individual nearest neighbors of this blue atom that I've identified here. And there are a bunch of different kinds of neighbors that I can have for this blue atom, right? I can have a blue atom surrounded by 4 blue atoms. I can have it surrounded by 1 red atom. I can have it surrounded by 2 red atoms. In this case, the 2 red atoms are sort of diagonally opposed to each other, or I can have them vertically opposed to each other. And then I can also have them surrounded by 3 different red atoms, right? So these are the kinds of configurations that are present in the system. And actually build a histogram, right, of the numbers of configurations. Again, this is all automated, and we'll do this in the notebook itself, right? We can find the 12 different kinds of configurations that are present here, and then I can build a histogram and try to find out what these configurations, what the probability is that in any one image, I'm going to find one of these configurations, right? So for example, trying to find a blue atom surrounded by 4 nearest neighbors of blue atoms, the probability is about 9%, right, in this particular image that I'm going to do that. And so you can calculate also error bars on this by getting multiple different images. But anyway, the point is that we can calculate these histograms purely in this data-driven way by just looking at the atoms themselves and building these histograms. So the next step is to then set up our model. So let's assume that we have some kind of simulation model, and we're going to have some parameters that we can tweak in that model. Well, then we want to tweak those parameters in that model such that we can minimize the discrepancy between the histograms that we compute from the simulation versus the histograms that we compute from the experiment. So let's say, for example, that this is our experiment in teal, right? So these are the probabilities of those configurations that I mentioned in the last slide, and we have a model, and we can sample from this model. I'll get to the model later, but let's say we can sample from this model, and we also get these sort of histograms, and again, they have some uncertainties involved as well. Okay, so what we want to do is we want to change the parameters of the model such that the histograms between the blue histogram and the teal histogram align as much as possible to within that error bar, right? That's what we want to do. And in order to do this, we need to compute a loss function. And the loss function that we're going to compute is the so-called statistical distance. And it is basically the arc length in probability space between these two different probabilities of individual states that we actually have, right? So let's have a look at what this equation is saying. So this equation is saying that, let's say that I have my probability vector P, which is basically a sum of these particular probabilities of these individual configurations, right? So I have each individual probability of obtaining these configurations. I also have the individual probabilities of obtaining these configurations from the simulation, right? So this is from the experiment, this is from the simulation. I want to minimize the distance S between P and Q, right? And so this particular distance is this arc length in this probability space, which is formed by basically taking the square root of the probabilities of each individual configuration and using that as your coordinate system, right? So when we do this, we can minimize the discrepancy between the simulation and the experiment and minimize the statistical distance S. And so this allows us to be able to use this loss function to be able to guide where we should change the parameters of our simulations such that we can minimize this S value here, right? So this measure actually equalizes statistical weights of these experimental and simulated data, and it correctly captures the fluctuations that are essential for any kind of predictive capabilities of our model, right? So if we use something like, well, why don't we just use a mean squared error between these histograms? You can absolutely do that, but you won't capture the essential fluctuations very well, and so it actually will fail for many cases. So you need to use the right loss function for the right system. And so in thermodynamic systems, you want to use this particular loss function here, okay? And the reasons why and the derivation for this are actually described in this particular JChem Phys paper that you can look at. So let's take this particular iron selenide telluride case, right? So as I mentioned before, what we are imaging here is that we are imaging the tellurium or selenium atoms that are on the surface with scanning tunneling microscopy. And so we wanted to create a very simple interacting solid solution model, right? So this solid solution model has bulk and surface terms, but basically there's an interaction term that tries to agglomerate atoms of different species types together, and so or repel them depending on what the sign is. And so we can change these interaction terms based on minimizing the distance between these histograms, right? And so that's exactly what's done. Again, you can look at the particular paper here for more details. But what we can do is that after we can very quickly simulate these different realizations and modify these parameters such that we can minimize statistical distance, we can then predict how this particular system should behave for different kinds of temperatures, for example, right? So we can simulate that, oh, when you change the temperature by a certain fraction, by a certain number, we can get a higher probability, for example, of seeing these blue domains sort of form, right? Compared to when we increase it further, when they start to split up a little bit more, and the red fraction seems to increase a little bit. So the point here is that we can start to use this generative model as a predictive tool that can then inform us how we should be performing our experiments in the future. And so that's really the power of this particular way, right? So we came up with a method where we could take an individual atomically resolved image, we could compute what the atomic neighborhoods were, right? Then we can use that in a particularly sound statistical distance framework to be able to match the theory with simulations and find the right interaction parameters, and also compare these interaction parameters with something that you might get from some kind of first principles approach. And in fact, it works pretty well, right? So even without a first principles approach, we're able to, just by making very simple models, come up and try to find these interaction parameters for this particular system. And in some cases, the first principles approach will also fail because it's not always very easy to predict some of these interaction parameters, particularly in strongly correlated systems. And I'll give you an example of that, and that's the example of segregation in manganites. And so, these are, again, images that we captured with scanning tunneling microscopy, but it really could be any kind of atomic resolved microscopy. But the point about these systems is that segregation of the divalent cation in manganite films is quite well known, right? And this actually presents problems for situations where manganites are used in devices, because as your device, if your device has segregation towards different interfaces, it's going to change the interface properties and therefore change the properties of the device. And so we would like to learn more about how segregation actually occurs in these particular manganite thin films. So here are some images that we captured on this manganite. This is an A-terminated or lanthanum calcium oxide terminated surface. You can see oxygen atoms on the surface here, and you can also see kind of vacancies that are actually present here. And in addition to this kind of atomically resolved data, we also have angle resolved, X-ray photoelectron spectroscopy data. So this can give us an insight into macroscopically what is the changes in segregation levels, right, of the cation, in this case, lanthanum and calcium, and how the calcium segregation actually changes as a function of distance, right? So if you're doing XPS and you have a very, very high, you have sort of a beam that's sort of normal to the surface, and you're going to be probing more of the bulk. But as you sort of change the angle of the sample, then you can be more sensitive to the surface layers. And so here we can model what the surface segregation is by looking at our XPS data and modeling that. So this gives us some idea about how individual layers are in terms of their overall composition. And then the STM gives us an example of the kinds of configurations that we have at our surface, right? So we have a bulk composition, we have surface layer compositions, and then we have an atomically resolved surface structure. So this is the kind of data that's available to us. How can we use our statistical distance framework to be able to merge all this data together to come up with a predictive model of this system? And that's what we came up with. So this is some work that we did a few years ago, where again, we take our previous image, we can do some we can find different kinds of configurations with and without oxygen here. And so we can actually see where there's oxygen and where there isn't oxygen. And we can come up with histograms. This is similar to what we did in the last case. But basically, we can see that there's a bunch of different kinds of sublattices of oxygen here. We can look at, lanthanum calcium atoms themselves, and we can compute the histograms of where these configurations are actually present. And then we can combine this, right? So we can combine this in a particular model where we have both surface terms as well as bulk terms to include interactions between the relevant species here, the lanthanum and the calcium and the lanthanum and the lanthanum on the surface, and then the lanthanum and the oxygen on the surface. So these are the ones that we care about. And these are the ones that should be relevant for the segregation in the system. And so we can come up with a loss function, which is the statistical distance squared, where we incorporate both the atomically resolved information, which comes from our configurations that we computed from those atomically resolved images, as well as the calcium concentration profile, right? So the profile of calcium segregation that we got from our XPS data. So this loss function accounts for both microscopic and macroscopic data, right? And so we can then compute this loss function and try to find what these interaction terms are based on minimization of this particular loss function. And again, as before, we can compute the histograms from the generative model and for the optimized model. And so these are the kinds of interaction energies that you get. And so these interaction energies have been compared for similar calculations from density functional theory, and it actually works pretty well, to be honest. It's a little bit better than even what we would have expected based on the statistics that we actually had, but it actually works really well. And so you can see, of course, that the histograms match relatively well as well for the local configurations, as well as for the calcium mole fraction that is predicted here versus what we actually measure from XPS. So we get very good matches between experiment and the model. And what we found from here is that really it's driven by sort of this segregation is driven by unfavorable electrostatic interactions between like cation pairs, as well as favorable elastic interactions as the calcium likes to migrate towards the surface. And so this actually results in sort of this tendency towards segregation. Again, this is just an example of how we can combine microscopic and macroscopic data to be able to give us meaningful physical insights into our system. And we didn't use any sort of density functional theory or first principles calculations to be able to compute this. We just did it from a data-driven model and from data-driven statistics as well as physics-driven models for just considering very basic interaction terms, effective interaction terms between relevant components in the system. And if we actually look at this particular generative model, we can, for example, look at the reduced free energy of segregation as a function of the calcium content. We can also look at, for example, the excess entropy of elemental segregation. These are sort of technical details, but this shows you that you can compute all of these things now that you have this generative model, right? So these are very difficult to compute normally otherwise. Another example is in the MOS2 system, which again, as I mentioned previously, we wanted to try to find out more information about this phase transition, but rather than doing it in a purely data-driven realm, as we did last time, here we can then apply our statistical distance framework system, right, to be able to find what are the interactions and what are the kinds of models that could explain what it is that we're actually seeing in this 2D material alloy system, right? So what are the different kinds of models that we can come up with? Well, we can come up with things like models which only consider the nearest neighbors or the next near. We can also have models which consider the next nearest neighbors, right? When you go out to the next nearest neighbors, are those relevant for us to be able to make predictions about the system, right? So we always have a choice whenever we have these images and we were trying to find our generative model. We have a choice in terms of the physics. That we want to look at, in terms of what kind of model that we choose, right? We can choose very simplistic models where we only consider the nearest neighbors, or we can consider more complicated models, such as many body models, where we're looking at interactions between sort of triplets, between, for example, in this case, molybdenum-rhenium triplets or molybdenum-rhenium triplets, right? And so we have interactions between those. But the point is that we can enumerate through multiple different kinds of models that could explain what it is that we are actually observing. And then we can compute statistics for all of these different models, right? So we can look at the individual kinds of models, right? So the red is sort of just a random model where we don't actually have any interactions. We have blue, which is the pairwise model, and then we have teal, which is the experiment. And so what you find is that, if you actually look at these different histograms of our different configurations at different compositions, the random model is sort of good at low and high concentrations, but it is not particularly good in between, right? So if we look at these red bars, they're not particularly close to the teal bars, right, for these intermediate compositions, right? So for example, this teal bar is quite high and the red predicts it should be quite low for these particular configurations. So this is clearly not working out very well. Now, the equilibrium model that we have, this pairwise model, is a little bit better, right? It's not perfect, but it is certainly better than random, right? So it's exactly what we would expect, right? We don't expect there should be random fluctuations here. There should be some kind of interactions between these particular molybdenum and rhenium atoms. And therefore, we do find that there is a better match for this pairwise model. However, of course, everything is within experimental uncertainty. What we really need is more data to be able to conclusively find which model is a better match for this particular system. And we can have a look at things like what is the probability that any of these individual models are actually the right model based on their likelihoods, right? So we can look at a 2-parameter many-body model. This is the loss energy landscape as a function of these 2 different parameters. You can see that the loss landscape is it's kind of broad, and this is generally not good. It means that we probably don't have enough statistics here to compare very well, and this model is maybe not the right model. The pair additive model seems to have a lower basin, so it's a little bit better. And there's a 2-parameter model which seems to work better than the single parameter model, but we need to quantify this, right? So should we move to a 2-parameter model, or should we stick to the single parameter model? And the way that we can actually do this is that we can actually find out, we can do some uncertainty quantification for these interactions. And there are many ways to do this. I won't expand on it here, but basically, you can read about it in our paper, but basically one example is sort of bootstrapping. We can just look at individual subsets of images and then calculate what are the histograms, and then calculate what is the variance on those histograms, for example. And so this provides an uncertainty estimate. We can also use sort of multi-color sampling to determine the probability of these particular interaction parameters given the data, with log likelihood given by the statistical distance squared, so that actually falls out from the math. But what about the model uncertainty itself, right? What is the uncertainty in these individual models? And so we can compute that as well, right? And so we can basically do hypothesis testing to find out which of the models are more likely than others, and we can use, for example, Bayesian information criterion approach to find what that actually is. Again, you can also read more about this in the particular paper, but the point here is that most of these numbers are pretty close to each other, which suggests that we need a little bit more data to be able to prove this conclusively. But again, it's also why I think it's very important to have theory in line with experiments, because if we were collecting the data while we were coming up with these different kinds of models, then we could have directed the microscope to capture more data so that we could be more confident in our hypothesis testing itself, right? And so this sort of gets at some of the bottlenecks that we have if we don't have automated and autonomous experiments that are coupled with theory for understanding interactions in many of the material systems that we are able to study with scanning, transmission, and electron microscopy. So in summary, I've shown you sort of a framework for analysis of atomic resolved imaging. First, I started with sort of very basic computer vision texture analysis. Then I moved to local crystallography and what can be done from a really data-driven approach. But really, if we want to extract the physics, then we need to move to physics-based models, and we need to be able to combine the best of the data-driven methods that can give us information about what's actually present and what's actually relevant for our image, and then compute that, and then compare that with physics-driven models with optimization techniques that I've shown here. And so by doing this, we can also get uncertainty quantification on the kinds of models that we can compute, and therefore give us the best possible model that can be useful for future simulations and for future experiments. And so if applied in real time, we can help to answer the question, for example, of how much data is actually required, right? So a very often asked question in electron microscopy is, when do I have enough data? And the answer to that is quantifiable, right? If you have a hypothesis that you are testing, you can quantify to within a particular kind of confidence bound. Okay, if I want 95% confidence that this is the right model, this is how much data I'm going to need, right? In order to be able to compute that information criterion to be able to tell you when to stop sampling. And so this can really be used for answering that question of how much data do we need. Okay, so before I move on to the Collab and describe the Ising model, were there any questions thus far? I don't seem to see any chat. Okay, so I'm assuming that there are no questions. So what I want to do then is that we're actually going to look at an example of how we can do statistical distance minimization, and we are going to simulate an experiment, right? So we are going to assume that we have a simulation model. In this case, the simulation model is the 2D Ising model on a square lattice. So if you're not familiar with the system, it's basically that you have a bunch of different lattice sites, and each lattice site has a spin up or spin down configuration. And you can, in this case, modify, for example, the interaction term, this J term, that couples adjacent spins together, right? And so we're not going to focus on the applied magnetic fields here. For now, we're just going to focus on this J term in our Collab. But what we are going to do here is that we are going to play with different values of J and see if we can compute a statistical distance minimization problem, right? Where we have a particular value of J in an experiment, and then we have a bunch of simulations at different J's, and we try to find what is the correct J that matches our simulations to our experiment based on looking at configurations that we would get from imaging this particular system. Okay. All right, so let's move to the Collab. So if you want to know where this Collab is, I will pop the link in the chat. Here we go. Here we go. So I'm going to give everyone a minute to get there. All right, so the first thing is we want to run this, assuming that you all trust me. So the first thing we're going to do is we're going to clone the Ising simulations, which are on my GitHub. And so this is just a very simple simulator that I wrote for the 2D Ising model. And it's very easy to use. All we need to do is we need to specify the number of lattice sites. So this is an n by n matrix. So if n is 20, then it's going to do a 20 by 20 simulation. And so we also need to simulate, we also need to draw from the interactions, right? So we need to, in this case, we are going to make a interaction matrix. And so each individual site is going to have that different value of J, but it's going to be quite small in its distribution, right? So we're going to center the distribution around 0.1 with a variance of 0.01. So in other words, almost all the interactions are going to be around 0.1 plus or minus 0.01. And then we just instantiate the Ising simulation. We choose the temperature. We also choose the number of equilibration steps and the number of Monte Carlo steps. You don't have to change this for now, but these are steps that you may have to change if you find that the simulation is not converging. If it's not converging, you need to move to higher values of these steps. So once we instantiate the model, we can run the simulation, and I'm just going to run it. Let's see how that goes. So we're going to use n equals 20 because I think that's a reasonable number. I think you can choose n equals 50. The higher the number, the longer the simulation takes. However, you will get better statistics with larger values of n, of course. Okay, so with the magic of Collab and number and a lot of acceleration, we can actually perform these simulations in relatively quick time. And what I want to do here is I want to be able to plot the results of the simulation for different time steps, right? So I've performed the simulation for 500 time steps. And so what I wanted to do is just to have a look at how this behaves over, over time. So let's have a look at that. So you can see, you can see exactly what's happening to the simulation over time by looking at these different configurations. So this is an n by n matrix, 20 by 20. And then there are, if you actually look at the size of this simulation, if I look at, for example, how do I do that? I look at the configurations shape. So for example, let me have a look at this. Dot shape. You can see that these are the results of the Ising model simulation give you something which is the length 500. And so the reason for that comes from the number of time steps you choose here, back up here. And then it's a 20 by 20 matrix. So those are the configurations that we have over time. So that's how the structuring works. It's very straightforward. And so what I want to do now is I know that there's a phase transition in an Ising model at a certain temperature. And so I want to be able to go across this phase transition temperature and see what my configurations look like. So what I'm going to do is I'm going to choose values of the reduced temperature between 0.5 and 5, and I want 20 different simulations. And I'm just going to save the results, right? And it's really easy to save the results by just appending to this particular list here by stating that I want to save Ising model.results, right? That's it. It's really straightforward. So let's perform this and let's see how long it takes. It might take, maybe 5 minutes to do all of this. So I'll just let you all play with that. By the way, you don't have to stick to my particular values here for J. For example, if you want to try 0.2 or 0.3, maybe change the scale a little bit, you can do that too. That's fine. Don't feel that you have to use this particular one. And if you have any questions, I'm happy to answer them now in the chat while this runs, as well as if you want to just unmute yourself, that's also fine. Okay, it's almost done. I apologize for the time. Should probably do it. So I guess while this happens, one thing we can do is have a look at the Ising model configurations that are actually present. So similar to the atomic resolved image that I showed of iron selenide telluride, we can look at the nearest neighbors. So here we're not going to consider the next nearest neighbors. We're just going to consider these four, right? Up, down, left, right. If you wanted to, you could actually consider the next nearest neighbors, which would be these diagonal elements. But for now, we're not going to do that. And it's not necessary for our particular model in any case, because we don't have those interactions in our model. So it doesn't really make sense to. But in an experimental situation, you could absolutely play with that too. So let's say that we have this sort of downspin and it is surrounded by other downspins, then you have that particular one kind of configuration. However, by symmetry, it is equal to if all of these were red, for example, right? So we basically can reduce the number of configurations by a significant number because many of these are equivalent, right? So if we have all red or all blue, then that's the same configuration. Similarly, if we have a single alternative spin on any of the four corners, then those are all equivalent. And similarly, if you have two of the alternative spins on sort of adjacent sites, then that's equivalent. So this would be equivalent when these two are on this side as well, or on this side, for example. So those are all the same. And similarly, if we inverted the colors, they would be the same. And then you have other cases where you have opposing ends being opposite spin. And so you can consider that to be a different configuration. And similarly, you can consider when you have three different sites, three adjacent sites being the opposite spin to be a different configuration. And finally, when all four sites are the opposite configuration. And so these are the 6 kinds of Ising model configurations that are actually present. So if we come back up here, I think we should be finished in terms of the simulations. It's probably the last one. Sorry, I ran a large number here because I wanted to make sure that we captured the region around the phase transition pretty well. Okay, looks like there's still one more to go. So anyway, coming back to these Ising model configurations, the question is, so how do we compute these from the images that we actually have of the Ising model? And of course, in your experimental case, that would just be from the atoms that you're actually seeing in your system. But the point here is that it's very easy to do this by effectively enumerating through all the possible configurations. And so in order to do that, the first thing I'm going to do here is I'm just going to make a utility, which is just going to make my figure of the kind of configurations that are being passed to this particular function. And so why might we do that? If I'm going to enumerate through all of the possible configurations, then I want to just visualize it quickly. And so this allows me to do that. So let's come back up here. All right, here we go. Okay, so clearly here what we see is the different configurations for different temperatures. And so at really low temperatures, you see that there's a single spin. So this is the fully magnetized state, ferromagnetic state. And then obviously, as you increase the temperature, you can see that, in fact, once you go to around, 3.5 or 4 in the terms of reduced temperature, you see that there's a sort of a large, fluctuation in your state, in your configurations. And so this is really because it becomes largely disordered here in the paramagnetic state. And so that's what's exactly occurring here. And so if you look at sort of the heat capacity or the energy, you can see, as a function of the reduced temperature, you can see this phase transition that's occurring. And you also see the peak in the heat capacity at this phase transition temperature, exactly as we would expect it for the 2D model case. But let's say that, okay, so we have all this sort of simulated data. And so this gives you an idea about where the phase transition is in the system. But let's say that, you have a particular experimental sample where you measured it at a particular temperature, and you don't know what the value is of the interaction parameter that you're measuring, right? How do we actually infer that? And so that's what we're going to do in the next part. But in order to do that, the first thing we need to do is compute what these configurations are in these particular images. Sorry, what is the probability of finding all these individual configurations in these images that we're actually obtaining from our simulations? So let's do that. And the way that we run that is I'm just going to enumerate through all the possible configurations. And so this took me, a few minutes, maybe 20 minutes on Saturday to write down all the possible configurations for the nearest neighbors. I've done it so that you don't have to. Basically, this is where all of the spins are, -1, and the last case is all the spins are 1, and then you have all the cases in between, right? So I'm just going to run this and let's see what it looks like. So this is going to just plot every one of those configurations, right? Okay, so you can see all of these 32 configurations and exactly what they look like. So obviously the first one is when everything is the same color, with the -1 spin state. And then here is everything with the +1 spin state. And then you have all of the ones in between, right? So of course, a lot of these are equivalent. And so what we want to do is we want to group these together by which ones are equivalent. And so we can, based on symmetry, we can group these together. And in fact, I've already done that here in terms of making a list of what configurations should be grouped together. So as an example, we obviously have to group together this configuration with this configuration because they're the same, except they're just flipped. So by symmetry, they should be identical. Now, of course, if you have a case where you have that symmetry being broken, then that's not necessarily true. But in our case, it absolutely is true. So we can group those together. And then similarly, we can group together, for example, 1, 2, 3, 4, because this is basically the same thing. It doesn't matter if your opposing spin is on the top side, left, right, or bottom side. They're all the same. This should all be the same energy, right? And so therefore we can group those together as well. And so we can repeat that exercise such that at the end of this, we'll only have 1, 2, 3, 4, 5, 6 different configurations that are present. So we have a histogram of size 6, right? So let's run this. And so now we want to or we want to assemble these groupings together, and then we want to be able to plot them. So let's plot them. And so these are the groupings that we're going to come up with. So configuration group 0, configuration group 1, configuration group 2, 3, 4, 5, right? So this is 6 because it starts from 0. So this is just sort of enumerating through the different configurations. This is really the most tedious part of doing this work. It's really trying to find out what configurations are the same or not. But as I mentioned before, I've done this for you. And so now that we have these configurations, we want to try to calculate the histograms, right? So given those particular images or snapshots from our simulation, can we compute the histograms? And so I've created this very handy function, which takes as an input the input image. It takes the groupings of the configurations as well as all of the possible configurations present. And then it tells you, or returns a normalized histogram of the counts of the number of each of these grouped configurations that are present in the image. So let's run this. And it works really straightforwardly, right? You just look through each individual particular lattice site. We look at its neighbors. We compare it to all the configurations to find out which one it corresponds to. And then we find out which group it belongs to. And then we can modify the histogram to basically add 1 count to that particular group and return that, right? So that's all we're doing here. It's normalized here because we normalize based on the number of configurations with number of sites that we actually have, right? So the sites are the lattice sites that we have, right? All right. So let's plot this. And so when I plot this, first I'm going to generate these configurations for different temperatures, right? So these configuration histograms for different temperatures, and let's plot what it looks like. And so you can clearly see here what's going on, that at low temperatures, obviously, the only configuration that we have is sort of the pure spin state. And then as we increase the temperature, you have some more fluctuations. And so you have some more of the other kinds of configurations that start to occur, right? So clearly something is happening between 1.45 and 2.39. So you would assume that there's some kind of transition occurring here, right? So are there any questions on that? Has everybody got to this stage?
Yes.
Okay, perfect. So with that said, the next thing we're going to do is, okay, this is all simulations, right? So we've just computed these histograms from the images that were given to us from the simulation. But now we're going to look at so-called experimental data, right? So this experimental data is going to have a different value of J, right? So we're going to presume that this experimental data comes from, again, the same kind of Ising model, but we're going to have a different value of J in here, right? And so maybe we can change the scale here. I don't know if it will make a big difference, but let's see. But the location, or in other words, the distribution from which I'm drawing J is now double what I initially calculated, right? So this is going to be the so-called experiment that we're looking at. So let's look at this experiment. And we compute it at a particular temperature. In this case, I'm going to compute it at T equals 3.16. All right, let's do that. And then now, again, we can compute the histogram for this particular experimental result. Let's have a look at that. We can do the same thing for the simulations at that particular temperature. So we have a particular temperature which corresponds to this, right? So 3.16 is basically this one here. Oh, okay, I think it changed here. So this is 3.11. So anyway, that's close enough. So that's going to be, let me redo this actually. Let me do 3.11 here because I know we have a simulation at the same temperature. So this is going to be, 5, 10. Okay, so this is going to be number 9. This is going to be element 10 and element number 11. So let's go with that. I'm going to run this again, sorry. And the simulation that I'm going to compare it to is going to be the one with the temperature at the same, right? So when we do that, at the same value, sorry, when we do that, let's plot them. Almost done. All right, so here we have what the simulation looks like and what the experiment looks like at the same temperature. However, you can see that in fact, these histograms look nothing alike, right? There's a significant, large discrepancy between our simulation and experiment. And why is that? And the reason for that is because this J value was doubled, right? And so we can expect different configurations in our experiments compared to our simulation. So how do we then find, what the J value should be in our simulation? Well, the first thing is we need a loss function to compute, and that loss function is the statistical distance. So this is just going to compute that for us based on inputting both of these histograms together, right? So I provide the simulated histogram and the experimental histogram, and then I just compute the statistical distance, which is really straightforward here. And then I just return this. And the distance here is 12.57, right? So that's quite large. So the next step here is we're going to have to redo the simulation with different values of J, some closer to the truer value, some closer to the values away from it. We're just going to give some, some numbers, and we're going to compute the statistical distance between the resulting simulation and the experimental distributions, right? So let's do that. I'm going to let you guys do that now. And I'm also going to try to do that. So, yeah, so you can follow along, or you can try to do it. I mean, ideally, you try to do it yourselves, but this is how I'm going to do it here.
Rama,
Yes.
how difficult would it be to go back and redo all of this for like a hexagonal system?
So it would require some adjustment of the source code because the source code is considering, a square lattice. But I believe that I think Mani Valetti may have, I think, a triangle lattice Ising model that he has also worked on. So that would also be available. So yeah, it's not, I would say that it is absolutely doable with the same underlying framework. You just have to modify the lattice class.
Okay. Okay, cool. Thank you.
Yep. All right. So when this finishes, basically what I did was as it shows, is I just changed the values of J that we are going to simulate between 0.05 and 0.4. And again, we use the same temperature as we got in an experiment, and then we're going to compute the histograms, which again, we just use the retrieve histogram function. And then I can also compute the statistical distance squared based on these different values of J and look at what it looks like, right? And so clearly here, right, so there seems to be a minimum for this around, around sort of 0.15 to 0.25, right? So remember, our experiment came from here, where, come back up here. The experiment was 0.2, so that's exactly where we expect the minimum to be. And so it's roughly around there, right? It's not perfect because obviously there's statistical, there's some variance in the J as well. And the experiment had a higher variance than we actually had in our simulations. And so that you're not necessarily going to have a perfect match, but you can see there's at least a minimum around where you expect it to have it. Now, obviously, if you want to get better in this minimum, then you shouldn't just, compute all of these J values across the spectra. What you should do is you should run it in an optimization loop. And so you can use a simple, coordinate descent or some other kind of, even Newton's method, some other kind of trivial optimization algorithm that's going to tell you like where you should move the parameter next to be able to minimize this statistical distance squared. But we just did this just to show you illustratively what the loss landscape looks like for different values of J, right? But yeah, so this is how you would go about trying to come up with a model and adjusting the parameters of that model to minimize the distance between the model and the experiment for image data, right? So this is the key distinguishing feature about all of this, is that unlike most theory experiment matching, here we are actually doing it for image data and we're not doing it for some sort of macroscopic measurement. And so you actually need to know what it is that you want to be able to compare, and the thing that you want to compare are these histograms themselves. I hope I've convinced you that this is a sound way to do this kind of experiment model matching. And if are there any other questions on this notebook? Has anybody had any difficulties with it? Has anybody played with more interesting values of J? All right, then. That being the case, I think that should close this Collab notebook share. if you have any questions about this particular model or anything that I discussed, feel free to shoot me an email. I'm always available, and I'm always willing to talk about science. So with that said, thank you very much for your attendance.